At this point, you've heard a lot of discussion of kinetics and reactions and how they work. Let me tell you a bit about mechanisms and sort of the underlying theory behind these rate laws. Okay, and so in a lot of these exercises, we've worked on determining from experimental data what the orders and the rate constants are for a reaction. So although you can determine them experimentally, sometimes it's actually possible to calculate them or predict them from first principles, just from like a theoretical understanding of this reaction. This requires a knowledge of how the reaction happens, or the way in which this reaction takes place, which is also known as the mechanism of a reaction. Most chemical reactions are thought to occur in a series of well-understood steps, and each of these steps is called an elementary reaction. So what happens in an elementary reaction is a relatively small number, maybe 1 or 2 or 3 particles, interact with each other to make some kind of product. So you say, all right, well, how does one particle interact with itself? It really can't, but maybe it breaks apart or dissociates. Okay, so if that happens, we'll talk about the molecularity of this step in this elementary reaction. So the molecularity just means how many things are coming together in one of these processes. A unimolecular step is when one particle just breaks down or rearranges. Bimolecular means that 2 particles are colliding with each other, and although it's rare, it does happen. You can have a termomolecular process where 3 things are in the same place at the same time, and they simultaneously collide with each other. But the vast majority of the reactions that you're going to see have elementary steps that are either unimolecular or bimolecular. If you know that a reaction is elementary, that's awesome, because what that means is that you can just look at the thing and figure out what the rate law is going to be just by examining the coefficients in front of everybody. Okay, so for example, if I know that this reaction here is elementary, there's only an A present, and it's A to the first power. That means that it's a unimolecular process, so the rate is equal to K times the concentration of A. Done. That's it. If I have A and B that are colliding with each other to make a product P, well, there's one A and there's one B, so the rate should depend on A to the first and B to the first. Okay, and there's my rate law for a bimolecular process. When chemists talk about the mechanism for a reaction, what they really mean is what's the series of all these elementary steps that together give you the overall sequence for this chemical reaction. So if I added up all of the elementary steps, I would get my overall chemical reaction. Because a reaction might have more than one step, there's usually one step that is, like, in some sense, the most important step. And the most important one we're going to talk about is the rate determining step. This is the slowest step in the reaction. And the reason that you want the slowest one to matter is because that's going to determine the overall rate of the reaction. So that's going to dictate how much product could be formed. Okay, you've heard this before, probably you'll hear it again. The chain is only as strong as its weakest link. Okay, reaction can only go as fast as whatever the slowest step is. It just can't go any faster than that. Okay, typically the slowest step in the chemical reaction has the highest activation energy. Okay, I'll show you a picture of what this looks like over here. Okay, for a certain chemical reaction, there's something called the Arrhenius equation, which says that the rate constant K is equal to some real constant A, pre-exponential factor, multiplied by e to the minus activation energy over RT. So the point is that the larger the A is, the larger the K is going to be, but the larger the activation energy is, the smaller the K is going to be, because it's part of the argument for this exponential term. Okay, and so if you had a chemical reaction like the one on the right, where there's actually 2 steps, right? The first one has this activation energy, and the second one only has this much activation energy. We would say that the first one, having the much larger activation energy, is going to have a much lower rate constant, so that's going to be the slow or rate determining step for this process. Okay. In the diagram that I just showed you, each of those minima corresponds to intermediates. That means that they can't really be isolated, whereas the maxima actually correspond to transition states. These are very unstable and not isolatable. Okay, so just to kind of emphasize that, oops. This point right here is the intermediate. This point right here would be a transition state. This point right here would be a transition state. When you're trying to come up with a rate law, it's usually useful to think about the mechanism for the reaction as being a series of these elementary steps. And sometimes you have to use certain approximations or equilibrium conditions to try to solve the process mathematically and sort of know what's going on. Okay, and so what I'll do in the next couple of slides is show you how you can derive a rate law from scratch. Before I do that, though, I do want to mention one thing. When we're doing all of this, it's really kind of sort of impossible to really prove that a mechanism is correct, okay, because you can't see these little particles moving around, okay. All you can really do is say that the data you're given is consistent with the mechanism that you're providing, okay. It's always possible that somewhere down the road, somebody somewhere is going to do some sort of experiment that leads to a different conclusion, a different mechanism, okay. And so it's possible to disprove a mechanism if the data doesn't seem to agree with it, but it's impossible to actually prove that a mechanism is correct. This is one of the reasons why kinetics and mechanistic studies in general is so difficult to carry out. Okay, so now let me give you a specific example. Let's say that I had a chemical reaction where A and B are combining together, and when they do that, they first form some kind of intermediate, which I'll call I, and then this intermediate is going to form a product P. Okay? And let's assume that the first step is an equilibrium. So that's what these two arrows mean, right, that I'm at equilibrium. This is sometimes called a pre-equilibrium because I have to do that first before the product can form. Okay, the only way that I can achieve a pre-equilibrium is when the last step is the slow step, which means that this first step has to be, relatively speaking, fast. So let's assume that the forward rate for the first step has a rate constant Ka, and the reverse rate going backwards has a rate constant Ka prime. Then I can say that pre-equilibrium will exist when Ka prime, right, the reverse rate constant is much, much greater, or the reaction is much, much faster than Kb, right? Kb is the equilibrium constant, excuse me, the rate constant for the second step. So if I just go back to this slide for a second, I'll fill in the values. So let's assume that you have rate constant Ka going forwards, Ka prime going backwards, and Kb is the rate constant going from the intermediate to the product. Okay, I can write down the expression for the equilibrium constant, right, capital K instead of lowercase k, products over reactants. So in this case, the product is intermediate I. The reactants are the A and the B. So that's concentration of I over the concentration of A times concentration of B. But I could also write it in terms of the rate constants, the little k's. Okay, and the reason for that is because I can say that the rate going forwards is Ka times concentration of A, and the rate going backwards is equal to Ka prime. This is A times B, and this is Ka prime times concentration of I. If I'm at equilibrium, the rate going forwards has to be the same as the rate that I'm going backwards. So that means that Ka times A times B equals Ka prime times I. And so I can just rearrange this. I over AB equals Ka over Ka prime. So that's where this expression comes from. If I look at what the product is doing, right, the rate of formation for making this product, which I'll call dP dt, the rate of change of product over time, that's based on the second step of the reaction. So that's equal to Kb times the concentration of I. So what I can do is use the expression that we just came up with, solve for the concentration of I, and then do some algebra, right, some rearrangements, and I can say that dp dt is equal to kb times I, but I know what I is. Okay, I was equal to, well, k is equal to I times A times B. So the concentration of I is really K times A times B, as I got this. And then I also know that K is related to Ka and Ka prime, right, the kinetic rate constants. So I can take that and shove it in here, and I get this. Point is that after all of this math, okay, I'm expecting a second order reaction, okay, because I have a rate constant, which is a bunch of little rate constants, right, Ka, Kb, and Ka prime. But more importantly, the rate depends on the concentration of A to the first power and the concentration of B to the first power. So this would be a bimolecular process, right? First order with respect to A, first order with respect to B, but second order overall.